Hello everyone, my name is Forrest Huang. Today I'll talk about our Kai paper on how to automatically mine macros from interaction traces that scale. This is a research work I've done during my time at Google in collaboration with Gang, Tao, and Yang. User interfaces and user experiences can be understood with many different types of abstractions. There is an abundance of recent research work at the Kai community that have looked at collections or datasets of user interfaces. In particular, prior work have looked at semantic classifications, such as annotating UI elements by their semantics that's functionally meaningful, discover and analyze design patterns from developer-defined UI views and activities, and using data-driven approaches to obtain embeddings beyond human-defined groupings. One rather important concept among these abstractions is the idea of macros, which is a set of actions that a user performs on a set of UIs in the app, with certain task needs and/or in certain contexts. Here's a macro where a user wants to scan a QR code for a Wi-Fi network. It is composed of 4 actions and 4 UIs that the actions were performed on, where a user would first click on the network button, click on the Wi-Fi icon, click on the plus icon, and then click on the QR code icon. Some of these macros are quite useful, but can hide under hierarchies of views in the app, such as this particular one that our system discovered. While there are datasets of existing user task annotations and recordings that can fit directly into our definition of macros, such as the amazing motif dataset here shown on the right, these datasets typically require a lot of human effort to collect and annotate, making them difficult to scale. On the other hand, automatic extractions were previously underexplored because it requires deep understanding of tasks and UIs that programmatic instrumentations or fixed UI concepts just does not cover. For example, a macro can span across multiple activities and views defined by developers, yet each view can support multiple macros. In this work, we introduced the first system that can fully automatically extract these macros directly from random or realistic interaction traces. As shown in this figure, the traces are passed through an LLM to extract tasks in multiple steps, and these traces also form an interaction graph to allow us to find a compact set of actions for the macros, and finally producing macros that represent user tasks and actions. In particular, the introduction of LLM have allowed us to overcome a lot of the challenges that's present in the past, since the LLM now has the basic knowledge of user tasks and interactions that allow effective identification and extraction of macros. To help you more easily visualize how our system works, let's walk through the process of extracting a macro from the Google Calendar app. To extract a macro, first, from an interaction trace of actions and UIs that were sequentially logged from random or human-curated traces, on each screen we prompt the LLM to extract the task that a user can perform. In this example, we have one of the many tasks from the Calendar app, and on this screen, the model extracted multiple tasks, and of which one of them is create a reminder. We also iteratively deduplicate similar tasks from the same app, which in this case adds a reminder that's extracted from another screen is considered the same task as create a reminder and was removed. Then for each duplicated task, we ask the LLM to generate the final action that completes the task. In this case, the LLM predicts that the save button needs to be clicked to complete this create a reminder task. We then ask the LLM if any additional information and parameters are required for the task. In this case, the title and the date of the reminder is required from the user to complete the task. After the task description, final actions, and parameters are generated from a particular screen, we then optimize the full set of actions to complete the task from the initial UI screen after opening the app. We construct a single interaction graph from multiple traces by combining similar actions of the same app, and find the shortest path in this interaction graph. In this case, we take a shorter path to complete the task using the path found from another trace as shown in the bottom. This is the entire walkthrough of the extraction process of a single macro in a single app, and our final result contains the natural language description, create a reminder, the action to complete this task, and the parameters required for the macro, which is the title and the date of the reminder to be created. Using the system, we have extracted a large number of macros from 2 datasets. First, from the rehearsal dataset that consists of 162,000 traces crawled by a random computational agent, we obtained 3,389 macros from 10 apps. Each macro contains 3.4 actions, which were optimized by 54.7% by our extraction pipeline. These results show the capability of our system when working with a dataset that crawls each app in great depth. On the other hand, we also extracted macros from the open source RICO dataset that consists of 4,189 human crawl traces. But these traces are from a significantly larger number of Android apps that test our system's ability to handle a large breadth of different types of apps. Our system extracted over 23,000 macros with 8.49 per app on average. Each macro consists of, on average, 3.41 actions and are optimized by 43.6%. So what do the generated macros look like? We dive deeper into a few more macros beyond those that we already showed you earlier in the presentation. First, this is a macro from the Settings app, which is to hide profanity in the live caption feature in Android. First, the user needs to click on the sound button, and then they click on live caption, which will finally expose the switch option to hide profanity. This is quite a novel macro task that all of the researchers on the team did not know the app could support, and this type of learning would be a good application that we envision our system can support. We also looked at another macro from the rehearsal dataset, which we extracted from the clock app in the Android OS. In this app, the system was able to extract the macro set the timer sound, where a user would first click on the three dots on the top right to reveal the settings button, and then clicking on the settings button enters the settings page, and at this UI, the macro contains a scroll down action that scrolls down the settings page to reach the timer sound option. This demonstrates the capability of our system to not only handle click options, but also swipe or scrolling actions that are commonly required to complete user tasks. Beyond the rehearsal dataset, our system can also handle third-party apps from the open source RICO dataset as mentioned earlier, such as extracting this View the Shop macro from the app of the American football team Tampa Bay Buccaneers. The system correctly extracted three actions to access the shop page, which is respectively clicking on the hamburger menu button on the top left, clicking on the fan page, and clicking on the shop. These actions are also not immediately obvious by first inspecting the landing URL of the app. And there are a lot of more examples of these macros in our paper, which we encourage you to read. Besides looking at extraction examples that demonstrates our system's capabilities, we systematically evaluate our systems in multiple aspects. First, we measure the quality of the task descriptions of the macros in natural language against human written tasks using established automatic text similarity metrics. We then execute the extracted traces to investigate whether the macros are correctly optimized and can achieve the defined tasks in the macros for our users. Finally, we conduct a user study to gather human feedback on the relevance, the reasonableness, and the novelty of the extracted tasks, and also comparing them against a baseline of human-curated golden tasks. Our first evaluation focuses on the quality of text descriptions of the extracted macros. So to ensure we have a trustworthy ground truth, we perform extraction on the UIs from the motif dataset that has human written task descriptions attached to UI traces as ground truths. And we compare the generated task descriptions against the handwritten task descriptions. Our method achieves a Rouge-L score of around 0.47 and a Meteor score of around 0.38, which is quite reasonable for systems performing similar tasks. To provide further reference of what these numbers mean, we implemented two baselines of which our system obtains significantly higher scores compared to both of them. These two baselines shows that our generated macro descriptions are specific to particular traces and UIs, and are adequate summaries beyond just reiterating the task content that's already shown on the UIs. While extracting the macros is the core contribution of our work, we further built a macro replayer to execute the extracted traces in a live environment to fully close the loop of our envisioned application of extracting and executing the macros. We additionally implemented fuzzy matching, and we skip invalid actions in our macro replayer to tolerate for errors or changes in the UIs. We deployed the replayer as Android emulators of Pixel 4 devices and run Android version 30 on them. We randomly sample 60 traces from the rehearsal dataset, and we are able to successfully execute 76.7% of them, which shows the vast majority of our extracted macros are valid and could be useful for the important application of UI automation. Finally, we also perform a user study to evaluate the perceived quality of macros with multiple criteria. We recruited 11 participants who have between 9 to 20 years of experience using smartphones. Among them, 2 participants are experts in app testing and are very familiar with the apps that these tasks are extracted from. We randomly sampled 60 macros from 3 apps in the rehearsal dataset and compared them against 60 handwritten tasks from the Pixel Help dataset, of which these tasks represents the human performance of our task. We show our users the task descriptions and the screenshots of UIs in each step of the task and ask them 3 questions for each task. First, we ask them if the task description matches the trace well, which measures the validity of the description and the trace. Second, we ask them if the tasks in the trace are reasonable for mobile users, which measures the reasonableness of the task in the context of the app. And finally, we ask them whether they can perform the task before seeing the example, which measures how novel the task it is for them. Our user study shows that while our system did not outperform human-curated tasks for both correspondence and reasonableness scores, both of the scores achieved by our system actually approaches pretty closely the ones attained by human-curated tasks. Moreover, over 70% of our macros also have the rating of 4 or above out of 5 for both correspondence and reasonableness scores, showcasing our system's ability to find tasks that are reasonable and relevant automatically. In addition, slightly higher percentage of our macros are unknown to our participants compared to human-curated macros, showcasing our system's ability to extract novel macros, which can be useful in how-to knowledge-sharing applications, such as automatic tutorial generation. We envision our work to support 3 major applications. First, with our newly extracted macro dataset, we can train agent models that can act on UIs and perform navigation and tasks based on high-level text descriptions. Moreover, our macro extraction method can enable LLMs to more easily interact with UIs in the natural language space, such that we can first extract all the possible tasks in the apps and allow LLMs to operate at the task level when interacting with users. These extracted tasks are also task shortcuts that can be created without any prior knowledge of the app from the user side. Finally, we believe the system can help users and developers share how-to knowledge in the apps, such as automatically generating task tutorials without extra effort. In terms of the limitations of our system, we believe there are 2 major limitations that warrant future investigation. First, we identified each of our UI states by the action elements ID and their surrounding element IDs. However, some of these IDs are reused between similar elements that have different functionalities in different contexts. This will lead to elements leading to the wrong states, such as a settings icon from the digital assistant app page here in the example would lead to the do not disturb page. An important area of future work is to investigate how to effectively and uniquely identify these UI elements, perhaps through dynamically incorporating context and or using learning-based approaches. The second limitation is that we make the assumption that all of the elements are stateless and will lead to the same UI whenever an action is performed on it. This is, however, not true in some cases, such as the switch here that switches off media sounds while the task is to allow media sounds. Keeping track and handling such state information is another important area of future work. So to conclude, we present the first system that can automatically extract macros that contain descriptions and actions of user tasks. Our LLM-driven system can extract meaningful tasks from app UIs and merge them into a compact and comprehensive set of macros. The macros extracted by our system are highly relevant to human-curated tasks and are reasonable and valid. Moreover, most of them can be successfully executed, which provides evidence for their efficacy in automation use cases. The macro datasets and systems can also support a number of important new applications in UI/UX research, such as interaction understanding, automation, and how-to knowledge sharing. And this concludes our presentation. Thank you very much for watching, and please do not hesitate to contact us if you have any questions.